Okay, this is going to be the video for Calc 3, section 16.8 on Stokes' theorem. And we'll start with a little review of Calc 3, chapter 16 up till now, because this is typically done after the winter break. This review actually is in the student notes, but it's at the beginning of 16.9. So if you want to follow on that, and then we'll come back to 16.8. All right. All right. In 16.1, we defined vector fields, the idea that at any point in the domain, we could define a vector that has magnitude and direction. Easiest to imagine this as a flow of fluid, a vector being a force that's imparted by the fluid, where these lines indicate the strength of the fluid and then the direction that it's moving in that direction. But they can uh, they can represent anything: electric fields, magnetic fields, other sorts of things. But anyway, it's just something where we've defined the input of a vector field. You can think of it as a function that takes an XYZ input and then as an output gives the vector at that position in the domain. Okay, so that's a vector field. In 16.2, we defined a line integral, which really should be called a path integral. That means that you can move along a path throughout the domain, and you get the contribution of the little forces of the vector that's in the direction by taking the dot product of that with the r prime vector, the tangent vector, which is in the direction. So it's adding up the component of the field in the direction along the path. That was the main subject of 16.2. In 16.3, we learned that the value that you get from a line integral usually depends upon the path you take through the field. Like if you go from a starting point to an end point along one path, you're going to get a different contribution sum from the fields as if you go along another path. But there are certain fields that are special. They're called conservative vector fields. And the test for that for a 2D vector field is if dp dy is equal to dq dx, right? And what's special about vector fields is that they're path independent. So as long as I have a starting point and an end point, if I sum the vector contributions along that path on any path, we'll get the same value. Okay. And then the other thing that happens is if you have a conservative vector field, then that means you can find something called the potential function, lowercase f, where the gradient of f is set equal to the field components. Right, so fx has to equal the x component of the field, fy has to equal the y component of the field. And this actually could be extended to higher dimensions as well, right? But the point is, if you can find this potential function and you have a conservative vector field, then you can evaluate the path integral or the line integral by using the fundamental theorem of line integrals that says it's just plug the endpoint values into the potential function minus plug the start point values in. Okay, so that was the subject of 16.3. In 16.4, we defined something called circulation, which was a tendency for a vector field, if you thought of it as a force field, to impart counterclockwise rotation, looking down on the path like that. Okay, so that was positive circulation in the direction that theta increases in polar coordinates or trig angle, and then negative circulation this way. And some fields have the ability to translate objects but not cause them to circulate, right? So we defined this idea of circulation and we came up with an expression for it, which was dq dx minus dp dy. And then we said there was a thing called Green's theorem that said that conceptually, if you're taking the path integral around a closed path through a 2D domain, then that's really a circulation, but it's really the summation of all the microcirculations that are enclosed. So instead of taking the line integral around a path, if it's a closed path, and then that means you can use Green's theorem to do a double integral of the circulations that are enclosed, right? It gives us a choice. You can either evaluate the line integral along all the segments of the path, which is kind of a pain if you say have a triangular region and you have to do that over 3 parameterized paths, or you can switch to adding up the circulations over the double integral. And often, even though this is a double integral and this is a single integral, sometimes the double integral is easier to compute, okay? That's called Green's theorem. The limitation on Green's theorem, though, is it only works for 2D. The field, the domain, everything has to be two-dimensional only, right? We really don't have an analog for that in 3D until 16.8. We're going to talk about that with Stokes' theorem. What we're going to cover that's new is Stokes' theorem is a kind of extension of Green's theorem into 3D. Okay, but to continue with our review here, in 16.5, we defined something called divergence in curl. Divergence is del dot f, curl is del cross f, and then the divergence produces a scalar at any point, which is a representation of how much the field diverges from that point. Positive divergence means there's a source of field lines, and negative divergence means there's a sink where the lines seem to be consumed, right? And then curl is like the 3D version of circulation, but it's actually a vector. And so what it is it points in the direction around which the field is circulating counterclockwise, right? Using the right-hand rule, if your thumb was in the direction of the curl vector, your fingers would curl in the direction of the circulation of the field. Okay, but we didn't do much more with that other than compute that. We'll start to use that with the curl here today. And then in 16.6, we talked about, okay, if we don't want to use a 1D path where we can parameterize with t, then we can parameterize a surface using u and v. And we spent a lot of time learning how to parameterize surfaces. And then finally in 16.7, we defined surface integrals where we could sum up all the values of either a multivariable function across that surface or all the components of a vector field that are perpendicular to the surface across that surface, right? And these are referred to as flux integrals when we do the vector version. Okay, so that kind of catches us up to where we were. So we're going to go on now to 16.8, and what we'll find out is that 16.8 is called Stokes' theorem, and like Green's theorem, it provides us a way to more easily calculate a path integral using a double integral. But this time, we're not going to be limited to only having a two-dimensional domain. So Stokes' theorem is really an extension of Green's theorem into 3D, okay? So Green's theorem stated that if you have a 2D domain and you wanted to find a path integral around a closed path, then you could integrate around the path, right, by doing the dot product of the path direction tangent vector with the field at every point in summing, right? Or sometimes it's easier to parameterize or to just take the circulation and then integrate it over the 2D region that's enclosed, okay? All right. And often that was easier to do. So what we're going to do to extend this into 3D is say that the thing that's like circulation in 2D is the curl of a vector field. Because if you take the curl del cross f, where you have p, q, and r, right? If you happen to have a vector field that was down here on the xy plane, this would just be 0, 0, and then the y or the z component would be dq dx minus dp dy, and so it would in fact be the circulation, right? So the curl gives you the circulation, but it allows that to be for a three-dimensional system, not just 2 dimensions for the domain, okay? All right, so if we put all that stuff together, then we can say, okay, f dot dr, Green's theorem said that that would be equal to the double integral of the circulation dq dx minus dp dy, right? But now we're saying in 3D, we're going to find that circulation by taking the curl and then the dot product with the normal vector of the surface. So it's a little bit more complicated. It's not simply the curl, it's the percentage of the curl vector that's perpendicular to the surface. So similar to this idea that you had to add up, um, um, you had to take a dot product of the field with the normal vector. Now we're going to take the curl to get this and then take the dot product with the normal vector to get the amount of circulation that's perpendicular, that's in the plane that's where the normal of that is perpendicular to the surface. All right. Okay, so Stokes' theorem says that the line integral around the boundary curve of S of the tangential component of the field, that's equal to the surface integral of the normal component dotted with the curl, okay? So just as with Green's theorem, this isn't an official, this is just kind of explaining the kind of meaning of what this means. As with Green's theorem, even though this requires using a double integral, often that's easier than working directly with the single integral along the path, mainly due to parameterization. Okay, so let's do an example from start to finish, and this should help us to see, what's going on here and how it works. Okay, let's say we have to evaluate this field f dot dr. We've got a field, we want to evaluate it along a curve, okay, and then the field is defined this way. This is a three-dimensional situation, 3D domain. And C is defined as the intersection of the plane x plus y, or y plus z equals 2, and then the cylinder x squared plus y squared equals 1, where C is oriented counterclockwise when viewed from above. Okay, so we could make a sketch of this situation, which would look like this, x, y, z. And we would have, well, let's do the cylinder first. The cylinder is a radius of one cylinder in the xy plane. So we have something that looks like this, right? Radius 1, cylinder. But then there's this plane y plus z equals 2. Well, y plus z equals 2 would be in the zy plane, something that had intercepts of 2 and 2, right? So you could think of it as being a plane that's up here like this at 2 and at 2. There's a plane that extends like this. And so where it cuts, it's going to cut, let me do it in red. It's going to cut kind of a diagonal cut like that. Okay, so that's the curve. It's the intersection of this plane, this green plane here, with this cylinder producing this red curve. That's the curve C. Okay, and then it's counterclockwise when viewed from above. So it's this direction. I guess I put too many lines on there. Let me back that off a little bit. Let's do it correctly like that. It's this direction right here. So that's our curve C. All right. Okay, so we're going to evaluate this, and we'll do that using Stokes' theorem. So Stokes' theorem says that as long as this is a closed curve, which it is, then that means we can instead find the double integral across the parametrized surface of the curl of f dot n across the surface. Okay. All right. So let's work on each of these things. Maybe we'll start with the n part because we're more familiar with that. We're going to need to parameterize the surface like we did in 16.7 to get its normal vector, right? Because we know that for a surface, the normal vector is RU cross RV, right? All right. So, so we're going to need an R vector. And the surface would really be, it's an elliptical disk, right? And it's going to be kind of the intersection of these two things. So let's actually intersect those two things. We have x plus y, or sorry, we have x squared plus y squared equals 1, but we also have y plus z equals 2, right? And so I think, yeah, if I were just to say, let's see, can I just parameterize? It's just the surface itself, right? So the surface is really, it's not, I mean, the boundary of it is being set by this, but really this itself is what's determining the surface itself. It's really just this plane. It's a portion of this plane. So this really is an expression for the surface. The x squared plus y squared equals 1 is giving me a boundary on that surface, but the surface itself could just be expressed as z is 2 minus y. So a convenient parameterization would be to have our UV be x and y, and then let x stay x, and let y stay y, but then say z has to be 2 minus y. Okay, so there's a parameterization. I don't know why my thing is wigging out here. There's a parameterization for the surface. Okay, the surface that's being enclosed, this part. Okay, and then I need my normal to that surface. So I'm going to have to take my two tangent vectors. So RU would be Rx in this case. And so we would take the partial derivative with respect to x would be 1, 0, 0, right? And then RV would be partial derivative with respect to y. In this case, it would be y. So that would be 0, 1, and negative 1. Okay, and then the normal vector would be the cross product of those two. So we have 1, 0, 0, and we have 0, 1, negative 1, plus minus plus, would give me the vector 0, minus 0, and then the negative of let's see, -1 minus 0, and then 1 minus 0. Okay, so that's going to give me 0, 1, and 1. Okay, that's my normal vector. So I've got this much now. Okay, now let's work on this, the curl of f. Okay, so for the curl of f, I've got my f defined here. I need to take the curl. So the curl of f is del cross f, right, which is going to be, let's put the field in here first, negative y squared x z squared. And then we'll load up the derivative operators, d dx, d dy, and then d dz, and then plus minus plus. So this is going to be a vector. And so it'd be the partial derivative of z squared with respect to y, which is 0, minus the partial derivative of f with respect to z, which would be 0, and then negative of the partial derivative of z squared with respect to x, which is 0, minus the partial derivative of negative y squared with respect to z, which would be 0. And then we would have the partial derivative of x with respect to x, which is 1, minus the partial derivative of y squared with respect to y, which would be negative 2y, so plus 2y here. So we would end up getting 0, 0, and then 1 plus 2y. Okay, and so that's this part right here. And so to build our double integral, we have to take the product of those two things and integrate that over the parameter region for the surface, because we're integrating over the surface. So we go down here a little ways. We're going to be taking the double integral of, well, let's figure out what curl f dot n is. So curl f is 0, 0, 1 plus 2y. And then n is this right here, 0, 1, 1. So it's going to be 0 times 0, 0 times, and that's going to be this times this, right? So it's just 1 times 1 plus 2y. So it's just 1 plus 2y. Okay, so that means we have to do a double integral of 1 plus 2y over some area, and that area has to cover the parameterization, so xy, for the surface. So to cover all these points on the surface up here, we're going to have to take the points inside the circle down here, which is a radius of one circle. Right, so if I'm covering that region down there, then that means I could choose polar. So we'll go with r dr d theta. And then it would be from 0 to 1 in the radius and 0 to 2 pi in the angle. And then finally, we would swap out this y. So the final setup here would be integral from, let me just change colors here, be integral from 0 to 2 pi, then an integral from 0 to 1 of 1 plus 2, and then for the y we have to put r sine theta, and then we have the extra r here, and then dr d theta. So this would be the setup, okay? All right. So that's how we would do this with Stokes' theorem, right? We instead of working this out by parametrizing the curve and then integrating along the curve the dot product, we're going to take the curl of the field and take the dot product with n, and then double integrate that over the area. Okay, so just to show that this is actually, even though this is a lot of work, this is less work than doing a parameterization of the curve and integrating f dot dr directly. In the notes, there is all the steps for that. Okay, what you would have to do, I'm just going to kind of go through it here fairly quickly, but you can read it completely in the notes. First of all, instead of parametrizing the surface, you would have to parameterize the red curve itself. Okay, so so if the curve of intersection is this and this together, right, you can substitute, solve this for y and substitute that into this expression to get this expression. So this is an equation for the curve in 3D space. It involves only an x and a z. Okay, since this term is squared, we could, if you wanted to, just swap these around and make that z minus 2. So this is an expression of a circle, but not at the center, right? Circle of radius 1 at offset. Okay, so for parameterizations, we've never really seen a case like this, but if you're interested, this is how you can handle an offset parameterization. What you can do is say, you know, if this was x squared plus, I'm going to say w squared equals 1, that would be a circle, and I know how to parameterize a circle, right? So if I temporarily replace this more complicated thing with another letter, then I can parameterize the x as r cosine theta and that w as r sine theta. And in this case, the radius is 1, so it would be 1 cosine theta. So x would be cosine theta and w would be sine theta, right? But we don't really have w as one of the variables. That was based on the fact that w is equal to z minus 2. So that means that z minus 2 is what would be equal to sine, and therefore z would be 2 plus the sine of theta. Okay, so x would be cosine theta, z would be 2 plus sine theta, right? And then y, y would have to be, um, back up here, 2 minus z to be at the intersection. So that would be 2 minus the 2 plus sine theta, so that would be negative sine theta. So by going back to the original expression of y, we can have a parameterization for x and z and y, and that means our parameterization could be just in terms of a single variable, because remember, this is a 1D path, so we have to get down to parameterizing for just one variable, and that variable is going to be the angle theta. So x would be cosine theta, y would be negative sine theta, and z would be 2 plus sine theta. And then if we allowed that theta to go from 0 to 2 pi, that would go once around the ellipse, okay? So then we would have to say, okay, that's my r vector, but we have to then take the derivative of that to get the tangent vector. So it's like t, but rt is a theta in this case, right? So you'd take the derivative to get the r prime. Cosine is negative sine is negative cosine, 2 plus sine theta is cosine. Then you have to parameterize the f. So the f was negative x, negative y squared, xz squared, and you'd have to replace that y would have to get replaced with negative sine theta, and that x would get replaced with cosine theta, and so on. That is this. Then you would have to take the dot product of that with this to get this. But then the final integration would be easier because it's only 1D. So we just have to integrate all that over the theta parameter going from 0 to 2 pi. Okay. And actually, this produces the same numerical result as what Stokes' theorem did. But, you know, I would subject that this is even more work. Okay. Now, sometimes Stokes' theorem does produce a 2D integral that's easier. Sometimes it doesn't. Sometimes it's easier to just evaluate the curve itself. So we'll take a look at other cases here too. Okay, so that's a first example in Stokes' theorem. It's really just a 3D equivalent of Green's theorem, if you want to think of it that way. Okay, but there's a kind of an interesting twist to it here. In Green's theorem, everything is in the xy plane, so there's one surface associated with this curve, right? But in Stokes' theorem, right, the surface is 3D, right? Could be 3D. Well, it is 3D. It could be curved like this, and then it has a boundary. So let me change colors here. What Stokes' theorem is saying is that if I have any closed curve in 3D space, closed curve that goes like that encloses like a boundary like that, then any surface attached to that, okay, that has the same boundary edge, right? If I integrate the curl dot n over that surface, I will always get the same thing as f dot dr around the boundary, right? Right, so both of these, Green's theorem and Stokes' theorem, allow me to find a 1D integral by instead doing a 2D integral. In this case, it's over a flat surface in the 2D plane for Green's theorem, but in Stokes' theorem, it's over a parametrized surface where we end up doing things in terms of du and dv, okay? All right, so that's the difference. And usually it's the double integral side that's easier, right? But it's not always true. Sometimes, I mean, they're saying these things are equivalent. Sometimes, if you're given for some reason a problem like this, it might turn out to be easier in rare cases to compute the path integral instead, the line integral, right? There are other cases where sometimes it's really easy to figure out what this normal vector is, and so it's easy to do the Stokes side, right? But rather than find the n with RU cross RV, sometimes we can find that easier. So on formula sheets, we usually include all three of these cases. Okay. All right, and then this is another weird thing, right? Unlike in Stokes' or in Green's theorem, where everything was in the xy plane, and there's only one 2D surface that the thing is enclosing, and now that we have a 3D domain, right, that boundary curve is the boundary curve for an infinite number of different surfaces in 3D, right? Like here's 4 different surfaces that all have the same boundary curve, right? And what Stokes' theorem is saying is that if you take a field and you integrate that around this curve path C, then that will be equal to the curl of f dot n integrated across any surface. This one, this one, this one, this one would all produce the same number, okay? Now that seems kind of counterintuitive because if you stretch and squash this thing, right, you're going through different parts of the field. But along with that, the n vector is changing, right? And so the components are always going to stay the same in such a way that when you sum them up over any field that's enclosed, then you'll get the same thing as doing a 1D integral around the curve, right? And so one thing we can do is sometimes they'll define a surface that's really weird, and we can say, okay, but by Stokes' theorem, since we're doing the curve, not the surface integral, we're doing the path integral, instead of doing this complicated one, why don't I just pick this one over here where the surface is a plane? Maybe it has a curve around it, but the surface itself is planar. So you can pick a convenient surface, okay? And we'll see an example of that here in a second. So we're going to do this problem 15 from the textbook. It says verify that Stokes' theorem is true for the field xzy if S is the hemisphere of the sphere centered at the origin radius 1, but only the positive y's, and then oriented in the direction of the positive y-axis. Okay, so to solve this problem, since we're verifying, we're going to calculate the line integral directly over the boundary curve, and we'll actually evaluate it all the way to a number since we're trying to verify Stokes' theorem. And then we'll calculate the surface integral of the curl over the surface as it's defined and verify that they both come up with the same thing. And then I'm going to extend this problem and say, let's see if we can pick another surface that would be easier to parameterize and integrate over than the given hemisphere and show that that one also produces the same value. Okay. All right. So let's start with the, well, where's the rest of my, well, this is it, I guess. Yeah. Okay. So I'm just going to copy this 3 times. Let me just clone this page and we will do 3 of them. Okay, so the first one we're going to do is directly. Okay, so if I'm doing this directly, then that means I'm going to evaluate this as do the integral of f dot dr directly. All right, so in that case, I guess I need to start with a sketch because we have to see what's going on so we can parameterize the curve. Verify that Stokes' theorem is true for this field. I'm not going to try to draw the field, but the surface is a hemisphere centered at the origin. So, and it's only the positive y's. So if I were to draw a hemisphere in here, radius 1, right, it's only going to be the positive y portion of that. So it's just this part down here on the xy plane, right? And then this part over here, this part of the hemisphere. Not a very good drawing. Okay, so the rightmost portion, that's that red part is what it's the surface there. Okay, so verifying Stokes' theorem means that we have to show that if I take this curve and integrate over that directly, it's the same as taking the curl of f dot n for this red surface and integrating that over the parameterized surface. So let's start with the green curve. Okay, how can we parameterize that curve? Well, that curve, the boundary of it is in the xz plane. Okay, so if I were to just draw the xz plane here, then that green curve, we'll stick with green, would be a radius 1 curve, right? And I could parameterize that as a circle. right? If I define my normal parameterization, if I define that as my normal parameterization, I would probably go with um, that that the radius is 1, and we're going to parameterize it with t being an angle, theta. So I'm just going to go with theta as the parameter. All right. So or if you like, we'll call it t, but it's really the theta. Okay. All right. So I'm going to parameterize the curve. I'll use green for that. R T, I'll call it that, but it's theta. Okay. Is going to be that x is always r cosine theta, right? So that means that the x here, the x would be r cosine theta, but r is 1, so that's just cosine theta. And then the y here would be r sine theta, which is just 1 times sine theta, but that's actually z, right? So the parameterization here would just be on the xz plane that that I have to have x, the x be cosine theta. Since on this plane y is always 0, y will stay 0. And then the z coordinate will be given by sine of theta. Okay. And then because we're more comfortable with t, let me just write that with it as a t instead. Cosine t, 0, and sine t. Okay, so we've parameterized our curve with t. All right, and that means that doing this, we're going to have to say that we have to take f dot r prime and then evaluate that over t, right? So we need the derivative. So r prime would be the derivative of cosine is negative sine of t. I'll use the t, and then 0, and then sine of t, the derivative of that would be cosine of t. Okay, that's r prime. And then I have to take my f and I have to parameterize that. So right now it's y, z, x. So going back here, this is x, y, and z from the r. That means that the y has to be 0. The z would be sine theta, or sine t in this case. And then the x would be cosine theta, or cosine t. So here's the field parameterized. And so if I take f dot r prime, then that's going to be the 0 sine t cosine t, and then the dot product with the vector r prime is negative sine t, 0, and cosine t. Okay, so that means this times this would be 0, this times this would be 0, and we'd have cosine squared of t. Right, so after all that, we end up getting cosine squared of t, and then we have to now integrate that. So we're going to take the integral of cosine squared of t over the parameter range, and to go all the way around this curve, we would have to go from 0 to 2 pi. Okay, cosine squared is not super obvious, so I would just use a table to look that up, an integral table. If I had to evaluate this, turns out to be 1/2 t plus 1/4 sine of 2t, evaluated from 0 to 2 pi. So you get your two copies, 1/2 something plus 1/4 sine of 2 times something minus the other copy, 1/2 something minus plus 1/4 sine of 2 times something. And you would plug in 2 pi over here and 0 over here. And when you're all done, that evaluates to pi. Okay. But that's for theta going in this direction, right? Which is this direction. Okay, but they said that this is oriented in the direction of the positive axis, y-axis, which means that the actual direction of rotation would be this. So this, the way we defined theta, the way we integrated was in the negative direction. So we have to make that negative. So this is negative pi. That's the answer. Okay. All right. So that would be what it would take to do it directly, not using Stokes' theorem, but just directly evaluating the curve. All right. Now we're going to use Stokes' theorem. So we'll do it over again. And this time I'll try to make a little bit better sketch. And we're going to do it actually over the surface as defined. So we have our hemisphere surface. I'll do it in red. It's this on the XY plane or the XZ plane with a part out here, right? But now we're saying, okay, although they're asking us to verify Stokes' theorem, we just showed that if we take the integral around the boundary curve, it turns out to be negative pi. What would the integral be if I integrated over this surface? Okay, that means this time I'm going to have to parameterize the surface. Okay, and we're moving towards using this as the way to compute it. The curl of f dot n and then over that surface. Okay, so there's no real obvious parameterization for n. It's changing at each point here. Like it's not just in a single direction. So my n is going to be RU cross RV. I'll have to pick some sort of parameterization for this surface, okay? All right, so we could parameterize in different ways here. One way, rather than try to solve this for z and figure out if it's positive or negative, which I think would work in this case because we could solve it for y, let's just go ahead and go with spherical, right? This is a sphere, so we should be able to parameterize with spherical. So let's do that. So let's do this. For the parameterization of the surface, our R, U, and V, let's make it that we parameterize in terms of phi and theta. So we can get to any point on this hemisphere surface by specifying its phi angle and its theta angle. Okay, and if we use the standard parameterization, that means that the x will be well, it's rho. The x is rho sine phi cosine theta, right? But since this is a radius of 1 sphere, this is just 1. So I'm going to go with x is 1 times sine phi cosine theta. Okay, y would be sine phi sine theta, standard transformations for spherical. And then the z will be the cosine of phi. Okay, so there's a parameterization. And that means we can take our two tangent vectors. The RU vector in this case would be R phi. So we'd take the partial derivative with respect to phi. So the sine derivative of sine is cosine, so it would be cosine phi cosine theta. And then same here, cosine phi, but this time sine theta. And then there, let's see, sine theta. And then the derivative of cosine phi would be negative sine phi. Okay, and then the RV, that would be R theta in this case. So go take the derivative, partial derivative with respect to theta. So the derivative of cosine is negative sine, so it should be negative sine phi sine theta. And then we've got, let's see, the derivative of sine is cosine, so it's going to be sine phi cosine theta. And then there's no theta here at all, so that's 0. Right? And then the normal vector is the cross product of those two things. So for the normal vector, we could load these up. We have cosine phi cosine theta, and then cosine phi sine theta, and then negative sine phi. And then over here we'd have negative sine phi and sine theta. And then let's see, we have sine phi cosine theta, and then we have 0. And then plus minus plus. So taking that vector, we're going to get, let's see, 0 minus negative sine squared phi cosine theta. Okay, that's this minus this. Okay, and then we'd have the negative of 0 minus sine squared phi sine theta. Okay, and then over here we'd have this times this, so that's going to be, let's see, cosine squared, but sine theta. So it's going to be cosine phi sine phi, and then cosine squared theta, minus this times this minus this times this, so minus minus is plus. That's going to be the same thing with a sine squared. So cosine phi sine phi, and then sine squared theta. Okay, which simplifies to, we have sine squared phi cosine theta, negative negative, so this is sine squared phi sine theta. And then here, I'm going to factor this out of both of these because that would leave a cosine squared plus sine squared, which cancels, so we end up with just cosine phi sine phi. Okay, that's the n vector. Okay, then we need to take the curl of f. Okay, so far this is not looking like a lot less work. Okay, and this is to prove a point, so bear with me on this. What's the curl of f? So let me switch colors here. I'll use red. It's yzx. Okay, so f is yzx. So what's the curl of f? Well, for that, we would have to take, we've got yzx partial with respect to x, with respect to y, with respect to z, plus minus plus. And so that's going to end up being, let's see, partial derivative with respect to y of 0 is 0, minus partial derivative of z, or z with partial derivative with respect to z is 1. And then the negative of this derivative, which is 1, minus this derivative, which is 0. And then this derivative, which is 0, this derivative, which is 0, minus this derivative, which is 1. So we would end up getting negative 1, negative 1, negative 1. So that's my curl of f. Okay, so the integral says I've got to take the dot product of this curl with this. So it's going to be negative 1 times this plus negative 1 times this plus negative 1 times this. So let's look at what curl of f dot n is. And that is negative sine squared phi cosine theta minus sine squared phi sine theta, and then minus cosine phi sine phi. Right? Okay. So then what we would have to do is integrate that over the parametrized surface, which is parametrized in terms of phi and theta. So we're going to be taking the double integral of this over d phi d theta. Phi is going to go from, let's see, from 0 up here to pi, and theta is going to go just from 0 to pi also, because we don't want all the way around the circle. We only want the part that's positive y. So they're both from 0 to pi. Okay. Yeah, definitely not less work than the direct method of this. And actually, we said we were going to actually integrate this. So let's simplify this a little bit here. We could say, since there's a sine squared here and here, I could factor out, get a little bit more room. We could factor out, we got 0 pi, 0 pi. If we took out a negative sine squared theta, what would be left here would be, actually, we probably want to leave that in there. Yeah, let's leave that in there because I think it would be easier to do it like this. We're going to have negative sine squared theta cosine phi. I'm just going to go ahead right now and break these each up into separate integrals because each of these terms can be done separately. And then I'm going to have plus another integral for this term, which is negative sine cubed phi. Nope, that's not right because a sine theta is sine. So it is sine squared. Yeah, maybe we should do it all. Yeah, I'm sorry. Let me back up. Let's just do these one step at a time. So if we're actually integrating this double integral, it's going to require iteration. So we could do the phi first. Let's do d phi. Okay. So we'll take the integral from 0 to pi of negative sine squared phi cosine theta minus sine squared phi sine theta minus cosine phi sine phi. Okay, and just do the phi part. That means that this and this are treated as constants. So if you use a table, you can look up that the derivative of sine squared, you get negative cosine theta as a constant, and the derivative of sine squared is 1/2 phi, let's see, minus 1/4 sine of 2 phi integrated from, let's see, now why did I do that from negative 0 to, oh, yep, one more change to make. No, that'll work, 0 to pi, that'll work. So we would go 0 to pi, and then I would have this integral here, which is the same integral except with different constants, so minus sine theta. Anyway, you get the idea. This is going to take another 10 minutes to do this. If you carefully go through all this work, and it's shown in the notes, dot, 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 you come up with negative pi, the same thing that we got over here, but man, is that a lot of work. So I don't think I've sold you on how Stokes' theorem is so great, right? So far, it looks like as much or more work to do the double integral side, okay? But Stokes' theorem has this idea that any surface that's enclosed by that boundary, you could integrate the curl of that over that surface. It doesn't have to be like a hemisphere. We could say, well, what's the plane that's enclosed, and pick that surface to integrate over. So here's where the beauty of it comes in. Okay, let me do this one more time. But this is the last problem for the video here. Okay, let me sketch this again. We've got our x, y, z. We've got our green curve back here on the xz plane, right? And we've got our surface out here, which is the hemisphere. And we just try to evaluate over this hemisphere, and it was a huge amount of work, right? But that green boundary also encloses this surface, that plane surface, just there on the xz plane. That would be much easier to parameterize, right? Because if I wanted to parameterize that, I could just say, all right, since I need it to be in the positive direction, right? It was in the positive y direction. Then that means that the curve has to be this way, right? In other words, let me use green. This has to be in this direction, because we had to do the negative when it wasn't in that direction. So what could I define as the normal in that direction, right? Then I could, the curl is not going to change, right? I went through all that trouble to find out that the curl of f, so I would have to do that whole step. I got -1, -1, -1. That wouldn't change, right? But what about the normal? So now it's easy to match the positive direction. The normal is just this vector here. It's just the vector 0 in the x direction, 0 in the y direction, or 1 in the y direction, sorry, and 0 in the z direction, right? It would just, we wouldn't have to find a position vector for this. We wouldn't have to take RU and RV, parameterize and all that. I just know that n to this plane, that's just a plane, the n is just always in the direction 0, 1, 0, right? So then I could use this form that says all I need to do is f dot n, or sorry, curl of f dot n. So let me back up and use black. This is 0, 1, 0. And we're just going to take the double integral of f curl of f dot n. Okay, so the curl of f is -1, -1, -1, and that would have required me to do this work. I would have had to do this red work, so a little bit of work to get that. Okay, but the n is just 0, 1, 0. And so the result of that is just -1. So all we're doing is taking an integral of -1 over this red region. And now that I know this is in the xy plane, I could just parameterize that as a radius 1 in polar, right? And just use r d theta from 0 to 1 and 0 to 2 pi. And so we end up getting that the integral of this is, let's just do this one. So we would have the dr part would be negative integral of 0 to 1 of r dr, which is -1/2 r squared, from 0 to 1, which would just be -1/2, right? And then we would take the theta part, which would be the integral of, it's just the constant 1/2 times the integral of 1 d theta from 0 to 2 pi. Should be -1/2 theta, 0 to 2 pi. It should be -1/2 times 2 pi, which is -pi. And that's by far the least amount of work of these three methods. Okay? So that's a really good example to illustrate, right? Stokes' theorem says that you can take, if you're trying to integrate an integral of a field, a vector field f dot dr across a 1D path curve in 3D space that is closed, you can either do the dot product of the tangent vector and the field across that, or you can take the double integral of the curl of f dot across the parameterized surface. But it's only going to save you time if you pick a convenient surface. Integrating that over even something as complicated as a hemisphere can be really challenging. Integrating it over a planar curve that's enclosed can make the problem actually simpler. All right, so that's where we're going to stop there. I realize that was kind of a really long video, but I think valuable, and hopefully that gives you enough to be able to do the homework problems.